Welcome! This video describes step response for series RC low-pass filter circuits driven by a voltage source. Step response is a zero-state response to a step function input, which is zero for all time before the rising edge.
For more technical background and insight on RC step response, please see this book, First and Second Order Circuits and Equations, available from John Wiley Sons.
The infinitely long leading zero voltage input in the step function definition corresponds to zero-state response, ZSR. Because any circuit transient voltages and currents decay to zero during the infinite time before the rising edge of the input voltage V sub s, we know that the circuit is in zero state at the time of the rising edge. ZSR means that all currents and voltages are zero when the input voltage steps up. For a series RC low-pass filter circuit, with the output voltage taken across the shunt capacitor, the output voltage step response is a rising exponential function. The output voltage, V sub out, asymptotically approaches the input voltage, V sub s, over a long time.
Question: what do the series RC resistor voltage and current look like?
Let's investigate. The input voltage, V of Vin, drops across the resistor and capacitor in series, like a voltage divider. But the voltage across the capacitor cannot be changed instantaneously. This means that at time zero, the rising edge of the step input voltage is initially dropped only across the resistor. In step response, which is a zero-state response, at time equals zero, V of V out equals zero. This means that for step response, at the starting instant of the rising edge of the input voltage, all the V of Vin voltage drops completely across the resistor because the capacitor voltage cannot be changed instantaneously. Over time, V of V out voltage develops across the capacitor. Solving KVL, Kirchhoff's voltage law, for resistor voltage, we get V of R1 equals the input voltage, V of V in, minus the capacitor voltage, V of V out. Solving for resistor voltage, V of R1, in terms of V of V in, we see that the resistor voltage in the right-hand graphic is a decaying exponential like a natural response. Notice in the green resistor voltage signal plot how all the voltage initially drops across the resistor when the input voltage V of Vin jumps up from zero rapidly. Over time, the resistor voltage decays away towards zero. Note that there is a 10 nanosecond delay in the LT-SPICE pulse function definition so that the rising edges don't sit on top of the vertical axis. Related to resistor voltage by Ohm's law, the resistor current has the same decaying exponential shape as the resistor voltage. The starting value of the resistor current is 50 milliamps, 1 volt divided by the 20 ohms of R1. The loop current depends upon the difference between V of V in and V of V out. The quantity V of V in minus V of V out gets smaller over time. The loop current fills the capacitor with charge, increasing the voltage V of V out. And finally, the RC time constant. At time equals RC, the output voltage has increased exponentially to 0.632 times the input voltage value V sub S. Thank you for watching and learning with us.